Good afternoon, everyone. Today, I'm excited to take you on a journey into a fascinating and crucial scientific field, photochemistry. Simply, but photochemistry is the study of chemical reactions that occur under the influence of light. It plays an important role in our atmosphere, environmental health, and even medical applications. Next. Before we dive into the fascinating world of photochemistry, let's take a quick look at what we will be covering today. Our presentation is structured into four main sections. First, introduction. We will begin by defining what photochemistry is and why it's so important. Second, photochemistry in the atmosphere. We will explore how photochemical reactions play a crucial role in our atmosphere, influencing everything from air quality to climate. Next, medical applications. We will shift our focus to the exciting ways photochemistry is being used in the medical field. And lastly is conclusion. We will summarize our key takeaways and discuss the broader implications of photochemistry in both environmental and health science. Next. So let's get started with our introduction. Next. What is photochemistry? At its core, photochemistry revolves around the molecules absorbing energy, typically from UV or visible light. When this happens, they enter an excited state, becoming more reactive and initiating a cascade of chemical reactions. This phenomenon is relevant to many everyday occurrences. Next. For then, I'd like to talk about photochemical smoke, one of the major environmental issues caused by air pollution. This type of smoke is a direct result of human activities, particularly the emissions from vehicles and industrial facilities. In large cities, it has become a persistent concern due to its negative impact on both human health and the environment. Photochemical smoke is a type of air pollution that forms when nitrogen oxide and volatile organic compounds react under the influence of sunlight. The key feature of this smoke is the formation of secondary pollutants like ozone, which is especially harmful at ground level, unlike traditional smoke, which is caused by smoke and sulfur dioxide. Photochemical smoke is more complex and sunlight-driven, making it more intense during warm or sunny days. Next. Now that we have understood how ozone is formed, let's take a closer look at why it matters. Ozone isn't just a chemical in the atmosphere, it plays a major role in both air pollution and climate change. Let's start with its effects on air pollution. In the lower atmosphere, ozone is a major part of photochemical smoke, especially in urban areas. This smoke significantly lower air quality and can cause serious health issues, such as respiratory problems like asthma and coughing. Over time, it can even contribute to heart diseases. So when we talk about bad ozone, this is what we mean. But in the upper atmosphere, ozone has a very different role. Here it behaves as a greenhouse gas, trapping heat and contributing to climate change. It can affect global temperatures and even weather patterns, showing that ozone is not just a local issue, it has global implications as well. So, in short, ozone links together human health, air quality, and the climate system, making it a key focus in environmental studies. Next, we look at the real-world impact. Um, Los Angeles photochemical smoke was first identified in Los Angeles in the 1940s. Since then, the city has become a classic case of smoke formation due to its high pollution, heavy traffic, and sunny weather. Even though pollution control laws have improved the situation, smoke still remains a problem in many large urban areas around the world. The health effects of photochemical smoke are serious. It can trigger asthma, cause eye irritation, reducing lung function and worsen respiratory diseases. This case highlights the importance of understanding and controlling photochemical smoke, especially as urbanization and vehicle use continue to grow. Next. Okay, the next part is for my friend. She will talk about the photochemistry in the atmosphere.
Okay, next. Okay, now I will talk about the role of the photochemistry in the atmosphere. Photochemical reactions are changes caused by sunlight. They happen in the air and affect many gases. These reactions have formed and break ozone, change pollutants, and affect the climate. Next. In the lower atmosphere, sunlight breaks nitrogen dioxide into nitric oxide and free oxygen atom. The oxygen atom joins with another oxygen molecule to make ozone. This reaction happens again and again during the day. It causes ozone to build up near the ground, especially in cities. This ground level ozone is not good. It is part of smoke. Next. Smoke forms with NOx and box react with sunlight. This makes harmful things like ozone, PAN, and aldehydes. Smoke often appears in cities with lots of car and hot sunny weather. It can cause health problems like eye pain, asthma, and lung damage. Next. Ozone in the stratosphere is good. It protects us by blocking harmful UV rays from the sun. But CFCs go up to the stratosphere and release chlorine. This chlorine destroys ozone. The worst ozone loss happens over an toxic. This is called the ozone hole. Next. Photochemical reactions connect the air pollution, human health, and climate change. Ozone has two sides. It is harmful near the ground, but helpful high up in the air. Also, ground level ozone is a greenhouse gas. It makes the planet warmer. Next. Satellites like chalk me watch gases like NO2 and ozone all over the world. Models like geoscam help us and help us understand how these gases change. They help us make better plans for air and climate. Science gives us helps to protect the air and fat climate problems. For me, it's okay.
Okay. In this section, we highlight one of the most prominent medical application of photochemistry, photodynamic therapy. It is a promising treatment that uses light and light-activated drugs to precisely destroy cancer cells. What makes it unique is that it combines technology and medicine in an non-invasive way while achieving effective results. Photodynamic therapy is a localized treatment that involves the administration of a light-sensitive drug known as a photosensitizer, which selectively accumulates in abnormal or cancer cells. Once the photosensitizer has been absorbed and distributed, the targeted area is exposed to a specific wavelength of light, commonly red or blue, depending on the depth of the tissue. This light activates the photosensitizer, leading to the production of reaction oxygen species such as single oxygen, which then destroy the disease cells. PDT is especially useful for treating superficial cancer, such as BCC and precursors lesions like actinic keratosis. Agents like 5-ALA and MAL are commonly used in clinical PDT treatment. The mechanism of photodynamic therapy involves a sequence of well-defined steps. First, the tissue is exposed to light, which activates the photosensitizer that has accumulated in the target cells. This causes the molecule to shift from a ground state to an excited state, single state, and then via inter-system crossing to a more stable troubled state. In this excited troubled state, the photosensitizer can follow one of the photochemical pathway. First one is PDT, transfer electrons to surrounding molecules to form harmful radical like superoxide anion or hydroxide radical. In type 2, energy is transferred directly to molecular oxygen, converting it into single oxygen, a highly reactive species. Both types of ROS induce cellular damage through membrane distribution, DNA fragmentation, and protein oxidation, leading to cell death by apoptosis, necrosis, or autophagy. Photodynamic therapy offers several clinical advantages that make it highly attractive compared to conventional cancer treatments. First, patients experience a short recovery time as the procedure is minimally traumatic. Secondly, the treatment is repeatable, meaning it can be administered multiple times in the same area without significant complications. Third, PDT is minimally invasive, requiring no surgical incisions, and often performed in outpatient setting. Fourth, it causes fewer systemic side effects than chemotherapy or radiation because it targets only the area exposed to both the drug and light. Finally, PDT has a high selectivity, affecting only the diseased cells while sparing healthy tissue. This is particularly beneficial in cosmetically sensitive areas such as the face and the skin. Clinical trials have shown up to 95% response rates in superficial basal cell carcinoma. Limitations. Despite its many benefits, PDT does have certain limitations that affect its clinical use. One major challenge is limited light penetration. Visible light, especially red light, can only penetrate tissue up to a few millimeters to 1 centimeter, making PDT most effective for surface or near surface lesions. Secondly, hypoxia within the tumor microenvironment is a common issue in solid tumors. Since PDT relies on molecular oxygen to generate reaction oxygen species, low oxygen levels reduce treatment efficiency. Third, delivering the photosensitizer may not always be effective, especially in tumors with poor blood flow or those located deep in the body. In these cases, the drug may not reach all parts of the tumor evenly, which can lead to incomplete treatment. Researchers are working on a solution like injection the drug directly into the tumor or using nanoparticles particles to help the drug spread better and reach the cancer cells more efficiently. In conclusion, photochemistry plays a vital role in both environmental and medical fields. In the atmosphere, UV light triggers reaction that forms ozone and smog, significantly affecting air quality and climate. Photochemical smog, such as in Los Angeles, remains a major health issue due to nitrous oxide and VOC reactions. In medicine, photodynamic therapy utilize light-activated drugs to target cancer cells with minimal side effect. As both a challenge and a solution, both photochemistry is central to understanding and managing modern scientific problems. That all was all from us. Thank you so much for listening.